Hi everyone, welcome back to Power Electronics session 6. Now we will discuss about the types of commutation circuits and a few of the commutation circuits we will discuss in this session. So these type of commutation circuits are whatever the classification I am going to talk about, those are based on what circuit we will use to turn on the commutation. But as I told you in a previous session, like I think session 4, broadly we have two types of commutation methods. One is current commutation method and voltage commutation method. All these circuits, what we are going to discuss, will come under either voltage commutation or current commutation. Okay. So let us start with the type of commutation circuits. So first one is like class A or load or self or series resonance or series capacitance commutation circuit. So most of the times we'll call it as load or self commutation circuit. This type of circuit we will use in inverters, series inverters. One, class B or resonance pulse or parallel resonance commutation circuit. Most of the times these type of circuits will be used in DC to DC converters or inverters. Class C or complementary pulse commutation circuits. Class C or complementary pulse commutation circuits generally will be used in HVDC system and all, like a circuit breakers. Class D or impulse or parallel capacitor or voltage commutation circuit. Again, this will also be used in DC to DC converters or inverters. Next, Class E or external pulse commutation circuit. This type of circuit will be used whenever you want to have a isolation between the commutation circuit and source, like actual source, which is supplying the power to the load. Okay, so that means generally we will have two different sources. One will be used for the load to supply the power, another one will be used for only commutation purpose, but most of the times we will not use because of the cost. But wherever you need the isolation, we will go for that. And last one is class F or line commutation. This is broadly simply called as a natural commutation. So these are different types. We'll discuss one by one and we will see that what exactly the meaning of each one. Load commutation circuit, that's nothing but like as I told you, this will be used in series inverters. So here load will be RL series load, or maybe sometimes you will have like a capacitor across the resistance and all. So different type of circuits will be there, but this thyristor will be torn off because of the load or because of its own load. That's why it is called a self commutation, or it is also called as a load commutation. So here once you turn on this, because this thyristor is actually like power biased by the source voltage, once you turn on this thyristor by giving the gate voltage, it is keep on supplying the power to the load. But how exactly this thyristor will be turned off, that is what we are going to discuss. That means with the help of this load current itself, this thyristor will be turned off. So assume this equivalent circuit, that means whatever the circuit we are taking, that will be equivalent of this one. Nothing but replace the thyristor for some movement with mechanical switch. Assuming this thyristor is acting as a switch. If you connect the RLC circuit across the DC voltage through the switch, how exactly the current will be flowing through that? That's what we need to discuss. Assume this thyristor or mechanical switch will be turn on at a t equal to 0, then current will be flowing through this. The current waveform in this circuit will be depending on the damping of the system. So as you might have discussed, as you know, like in general, we'll have 4 different type of damping circuits. That mostly depends on the resistance value. So that's what we require here, but we'll discuss some extent what exactly is required. So here assume no damping in the system. That means no damping in the system is like undamped system. Okay, undamped. Undamped is nothing but resistance is 0. So you will have only inductance and capacitor. In that circuit, current will be like once the switch is turned on, current will be like flowing through the switch or thyristor or load will be like a exactly sinusoidal waveform. That's nothing but undamped sinusoidal waveform. When it comes to underdamped system, underdamped system, you know that delta will be less than 1. We'll discuss what exactly the del etc. and all, but now it's underdamped system. In that case, current flowing through the switch or load will be damped frequency of oscillations. Nothing but this will be dies down to 0 at t equal to infinity. Okay, so that's the meaning. Then move on to critically damped system. In case of critically damped system, del equal to 1. So in this case, current will be starting from 0 and increasing to max value. After that, it will keep on reducing to 0 and it will meet the 0 at t equal to infinity. Same way, you can also look at that other one, that's nothing but, and fourth one is nothing but overdamped system. In case of overdamped system, del will be more than 1. In this case, it is like a current waveform is more or less same as the critically damped system, but it takes more time than the critically damped system to reach the 0. So that's what, like it will also reach the 0 infinity. So these are the things, like when you are actually assuming that in the like a RLC series load is connected to the DC source through the mechanical switch, nothing but switching action, then current waveform will be decided by the damping of the system. So that's what we discussed. Now if you combine all these waveforms on a single graph, you can see that the current flowing through the inductive load, RLC series load, if you combine all these waveforms on a single graph, then you can see that current flowing through the RLC series circuit for the different damping systems will be like this. That means blue indicates undamped system, then red indicates the underdamped system, black indicates it's like a critically damped system, and gray indicates overdamped system. That's the meaning of it. But in this case, you can see that once the thyristor is turned on, this current starts flowing through that. In which case, this current coming to 0 quickly. Okay, you can look at the waveforms and you can see that this current is coming to 0 quickly first with undamped system. So you can see that here it is happening with undamped system. Okay, undamped system. Next coming to 0 with underdamped system. But in case of critically and overdamped system, this current never come to 0. That means if you want to commutate the thyristor in case of load commutation, either load must be undamped load or underdamped. Based on this conclusion, if you want to turn off the conducting thyristor in case of class A commutation circuit, load must be either undamped system or underdamped system. But as you know that in general, you never see the undamped system practically. That means we can conclude that if you want to turn off the thyristor in class A commutation effectively, then load must be underdamped system. That is what we need to look at that. Load must be underdamped load if you want to commutate the thyristor in case of class A commutation. So that's what. But however, we will discuss both the cases, nothing but undamped system, underdamped system. So undamped system is theoretically we can use that is for like a kind of like our solve the gate exam questions and all, but both will be, as I told you that for purpose of like gate exam, like As I told you, for the gate exam purpose, we can also discuss that undamped load. Undamped load is nothing but we can see here, we can actually have only L and C. But remember, in case of class A commutation, capacitor will not be charged initially. That's what you need to remember all the time. Okay, so now here you can look at that. Thyristor is forward biased by the source voltage. You can turn on this thyristor whenever you want by giving the gate voltage. Then the current flowing through the thyristor will be like this. As we discussed, it is an undamped system. That's why output current will be nothing but load current, or thyristor current will be like this. It will follow the sine wave. It will follow the sine wave. Okay, so now we can see that you can ask that why I'm actually drawing the rest of the part in dotted line, but why this is in the solid line. So that means here we discussed everything in the previous things and all, like a mechanical switch that will allow the current in bidirection, but here thyristor means that will allow the current in only one direction. So once you turn on this thyristor, current will actually increases to max value, then come to 0. Once this current comes to 0 below the holding current, then the thyristor will be turned off. That means ideally this will be turned off at 180 degrees. So after that, the current try to flow in the reverse, but it will not allow. That means thyristor will be turned off. So that means here thyristor will be in conduction for this duration only. That duration is nothing but T. So okay, you can use the small t. So that T is nothing but, you can see this will be nothing but omega naught T. Okay, that omega, because this is the frequency is nothing but resonance frequency, that's why omega naught T. That is equal to how many radians? We know that 5 radians. So that means in case of undamped system, thyristor will be in conduction for T seconds. That T is given by pi by omega naught, and we know that omega naught is nothing but 1 by root LC. Then it will be pi into root LC. Okay, so that means in class A undamped system, once the thyristor is turned on, then thyristor will be in conduction for pi into root LC seconds. So this is the equation for undamped system. Likewise, we can actually look at the underdamped system. Underdamped system means resistance, inductance, capacitance, all will be there. But here, denominator of the second order system will be like this: S square plus R by L S plus 1 by LC. So from this, we can take that like a del. How to take the del? Del is nothing but like a, maybe you can compare with this one, with the standard second order system, like S square 2 del omega naught S plus 1, omega naught square. Okay, so if you compare this one, then 2 del omega naught equal to R by L. Okay, so from there, what will be the del? Del is nothing but R by 2L omega naught. But by comparing these two, omega naught is nothing but 1 by root LC. So it is in the denominator, then root LC comes to the numerator, R into root LC by 2L. So that means damping ratio for the second orders RLC series circuit will be R by 2 into root of, see, root L gets cancelled, that's why it is C by L. But as I told you that it should be work for the underdamped system, then it should be less than 1. So this is the condition we need to take for the class A or self-commutation system. That means it can give like maybe like sometimes it will be given that R and L value, then we need to calculate what should be the C value to have the commutation for the circuit. So that's why we need to remember, or otherwise you can take that R must be less than 2 times root of L by C. Okay, so that can also be taken. Okay, so any one of these we can use that. So That's where we can actually look at that. So now if you look at this one, like now if you look at underdamped system, if you turn on the thyristor at t equal to 0, then output current will be, okay, as we discussed, it will be a damping current. So then it will be something like this. Okay, it will be damped to 0 at t equal to 0. But as I told you that this dotted line is because once this load current comes to 0, then thyristor will be turned off. That time we need to find out. Okay, so in case of underdamped system, so the frequency of oscillations will be omega d. So omega d, this I am taking as a small t, don't worry, omega dt equal to 180 degrees or pi radians. From this, the time in which thyristor will be in conduction will be pi by omega d. As you know that in case of underdamped system, damped frequency of oscillations will be like a omega naught into root of 1 minus del square. Remember these two equations for underdamped system.